This is a micro lecture about dealing with dichotmous outcomes. The basic problem is simple. We want to relate a continuous variable, which can either be a latent trait or an independent variable in a causal analysis, to a dichotmous outcome variable. Now, the first example relates to a latent trait. Suppose that we want to measure mathematical knowledge and we want to use items to measure this mathematical knowledge. The items are often incorrect correct items, so dichotmous items. And we want to see whether there is a relationship between the latent trait and the dichotmous outcome. The second example relates to independent and dependent variables, so to causal analysis. Age, years, can be related to the decision to vote or not to vote in an election, so also a dichotmous outcome variable. Now, normally we want to estimate linear functions. So we want to estimate a linear relationship then between the latent trait and the item score, or between the independent variable and the dependent variable. Most of the time, the item and the dependent variable are ratio variables. So for the time being, let's assume that the item or the dependent variable is continuous, so a scale or a ratio variable. Then the linear relationship looks like this. There is an independent variable, or the item, a latent trait, or the independent variable, is the x variable, and we try to find a relationship like this, where b0 is the constant and b1 is the intercept. Now back to the problem. Suppose that we have a dichotmous outcome variable and a latent trait and an independent variable. Then all our observations will be here or there, but nowhere in between. So now we have a problem, because if we want to estimate a line here, then even if the relationship is very strong, we will have a lot of errors. So suppose there is a very strong relationship between our latent variable, or our independent variable, and the outcome variable, which is dichotmous. So it looks like this. We are very sure, for example, that young people never vote and old people always vote. Now, if we want to estimate a linear equation here, then we've got a lot of errors, like here. And of course, we also estimate that some people that are, say, 30 or 40 years old have a 50% something of voting. That's impossible, at least if we take it as a dichotomy. No matter what we do with our linear equation, we always have a lot of problems, no matter how good the quality of our theory is. So we've got a problem here, and how do we solve that? Now, statisticians have solved that by changing the dichotmous variable into something which is, well, less easy to understand. But after changing that into something which is less easy to understand, we change it back, and then we can easily interpret it. So to summarize our problems, if we estimate a linear relationship between a ratio variable and a dichotmous variable, then the prediction line is also between 0 and 1. The prediction line extends below 0 and above 1, while of course there are only observations at point 0 and 1. Now, solving the problem of having dichotmous variables is done in a few steps. The first step is thinking in terms of probabilities, proportions. We no longer think about the variable as simply dichotmous, but as a percentage of people answering the question in a specific way. And then we change these probabilities into the odds. We take the natural logarithm of the odds. If you don't know what the natural logarithm is, check your calculator. And finally, we interpret the outcome of the analysis, because we now analyze the relationship as predicting the natural logarithm by a linear equation. We interpret the outcome as being probabilities. So we interpret the whole thing back. So first from yes to no to proportions. So what's that first step look like? Well, P is the chance of giving a correct answer, or the proportion of people giving the correct answer, which is in most circumstances more or less the same thing. So I, at least in my head, mix the two up all the time. So suppose that we've got a latent trait here and an independent or dependent variable, then we can think of proportions of people giving 1 or 0 as the answer. So 5 people give, say, yes here, or the correct answer, while 95% of the people at that position on the latent trait give the wrong answer. And we can do that for all groups. Now, instead of using 0 and 1, we use proportions. So the first proportion here is 5. It's positioned here. The second one is 5. Then we've gone 30, okay, 70, 95 and 95. And now we see something which is a bit closer to a line. So maybe this is the thing we need to estimate. Not the 0 and 1, but the proportion. And we can estimate a line. But we still have a lot of problems because we see here that if we estimate a line here, we can predict more than 100% and less than 0%, which is not what we want. So in between we have more or less solved the problem, but we are still left with the problem over 100 and below 0. The second step we then take is that we change the probabilities to the odds. And odds are defined by p divided by 1 minus p, or q. So for example, if the p is 50, so 50%, so 0.50, the odds are 1, 50-50. If p is 0, then the odds are 0 too, 0 divided by 1. If p is almost 1, the odds are infinite. Now this is something we like, because we are now no longer bound to the upper end of the scale, so we're no longer bound to 1. If the p is 0.95, the odds are 19. Now we first change the probabilities to the odds. Okay, the odds of 50% is 1. Okay, so you see it on the left-hand side. If the odds of 95 over 5% are 19. And you can imagine that in between infinity and 19 there are a lot of numbers that are predicted. So what happens here is that the line that we estimate, if we estimate the line between the latent trait and the independent variable and the dependent variable, bends off. Okay, and we no longer have predictions above something, because we can never predict something more than infinity. But we haven't solved the problem there. And by taking the log of this number, we can solve that problem too. So we go from the odds to the log odds. We transform the variable in more or less the same way as we did by transforming the probabilities to the odds. And by taking the log, we can have the full range of values available. Now, the log odds of the 50-50 chance, so the log of 1, is 0. So that's now the middle point of our scale. We can now say the log odds gives us a variable with many values between minus infinity and plus infinity, and that variable acts like a ratio variable. So now we can relate the independent variable, which is a ratio variable, to another ratio variable. So we have transformed the dichotmous variable by 2 steps into something which is a ratio variable, which ranges between minus infinity and plus infinity. The log of a very, very big number is still a very, but slightly smaller number. The log of 1 is 0, and the log of almost 0 is minus infinity. So we have that variable between minus infinity and plus infinity. What does it look like? Well, like this. The log odds are plotted at the left-hand side. And you see that we are now able to estimate a relationship that looks like this. Now, does this mean that we are estimating a linear relationship? Well, actually, yes. Because look at the scale there. It's not really a ratio scale anymore. Because we have indented the top and the bottom. We have to stretch that out, and if you stretch it out, you also stretch out the line on the right-hand side, and the same is true for the bottom line on the right-hand side. So by stretching that the y-axis, we are back to a linear relationship. So we go from the odds to the log odds. We now have transformed our dichotmous variable into a ratio variable, which we can predict. We can make a prediction of the log odds, so that's what we do. We predict with a constant and an intercept the log odds of something. So that's what we do when we estimate a relationship between an independent and the dependent variable. That looks like this. So we can now make statements like, if the latent trait is 10 or if the independent variable is 10, the log odds are 2.94. which means that there is a chance of 95% of answering correctly or 95% of voting in an election. So that's exactly how we interpret the log odds. We estimate an equation, a line, and we get something like log the chance that an answer is correct is, and here is the equation. Well, what does it mean? Well, it means that if the mathematical, that first of all, the effect of mathematical knowledge on answering an item correctly is positive. There is a plus there. And secondly, if the math knowledge is 50, so we got a scale and it includes the value 50, we just plug that into the formula and we get 0.9. So we now have a prediction of 0.9 of the log for the log odds. Well, what are these log odds? This is the relationship between the log odds and the probability. 0.99, here 71%. What have you learned watching this micro lecture? You've seen that linear relationships can also be used when dealing with dichotmous variables. We just have to change the dichotmous variable into something called log odds. We first transform the dichotmous variable into something which has to do with probabilities, then we transform it using the idea of the odds, and then we take the log odds and we try to predict that log odd. Finally, of course, we have then to interpret the relationship between the log odds and the independent variables that we have selected.